It's now on.
Okay, hi. Welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at a second-order differential equation and resonance. So here's our equation. Our problem that we're going to take a look at is we're going to solve ay double prime plus by prime plus cy equals e to the ct. Okay, so this would be exponential resonance, and it would also apply if you have a complex solution. The same thing would apply with a sinusoidal answer as well. So what we're going to do then is we're going to do this. We're not actually going to work on this solving it, because we know that our solution is the form of something like you need a different letter. How about okay, this a here is not that a, but we're going to need this e to the at plus, it's not that b, but b e to the bt. Okay, these are just some constants. I could use a C1 and C2, but we're going to be using these letters a lot, and those get kind of hard to keep track of. So what this means is that if this is a solution to my null equation, that means that if I was to write my differential equation as some polynomial, let's write it this way, as a d squared plus b times d plus c times y. Now I have it as a polynomial in d. And so this would be my differential operator, or I'm going to just look at it this way. So now I have p of d times y equals e to the ct. So now we have the notation that we're going to need. What this means is, since this is a null solution, what that means is it means that if I take my polynomial and I plug in lowercase a, that's going to make this equation here 0. It's one of the roots. So that's going to be 0. And likewise, if I plug in lowercase b, that'll also give me a 0 to my polynomial. So what we want to do is we're going to remember this. Our next piece is our y particular. And our y particular is of the form, we said it was e to the ct over p of c. Like that. So our complete solution happens at the y null plus y particular, and let's write this out. This is a e the at plus b e to the bt plus e to the ct over p of c. Okay, that's my complete solution. Now, resonance, our author calls it a very particular solution. And resonance happens under the conditions when our initial condition is 0 and y prime of 0 is also 0. So the whole system starts at rest for both its distance and its velocity, and then everything is going to begin moving exactly together. That's what resonance is. So what we need to do is we're actually going to find this very particular solution. So what we're going to do is we're going to evaluate y of 0. So y of 0 means I'm going to put a 0 here in this t, and a 0 here. So if I do that, that's going to give me that y of 0, which is equal to 0, is equal to, then this is just going to be an a plus b plus 1 over p of c. So a plus b plus 1 over p of c. Again, let's do this. Y prime evaluated at 0 is also 0. Let me write that out. Let me write y prime first and make this easier. We don't have to do this in our heads. So y prime is going to be then lowercase a e to the at plus capital B lowercase b e to the at, and then when we take the derivative of our particular solution, we're going to have plus c e ct over p of c. Okay, so then let's find out what y prime at 0 is. Well, it's equal to 0. And what happens is my exponential terms become 1. And so I'm left with capital A lowercase a plus capital B lowercase b plus c over p of c. Okay? Now, oh, look at this. We have a system of equations. Our system of equations are a plus b plus 1 over p of c equals 0, and a lowercase a plus b lowercase b plus c over p of c equals 0. Let's just, for a little notation and to keep track, we'll call that equation 1, and let's call this equation 2. Let's take, oh, I know what we'll do. Let's multiply equation 1 by a. And that'll help us, then that'll give us a b. So I'm going to write this as, so if I take a and I multiply it by equation 1, that's going to be aa plus ba plus a over p of c still equals 0. And then just for clear, then what we're going to do is let's take a times equation 1 and we're going to subtract equation 2. So I have aa here. So I'm going to subtract the aa over there. That's going to give me a 0. Then I have a ba here, and I'm going to subtract this. So that's going to give me a ba minus bb, and then I have here a over p of c, so plus a over p of c, and I'm going to subtract from it, c. So c over p of c. Oh, look, now we can just find b. So I'm going to do a couple things. I'm going to, equals 0. It still equals 0. I'm going to combine these two terms. I'm going to move them and put them on the right-hand side, and I'm going to factor a capital B. So this becomes capital B, a minus b, parentheses, equals, I'm going to write this as a c minus a and I'm going to move it over to the other side. So I have a minus c minus a over p of c. Okay. Then, now we can find a. So let's use, we can use either of those equations. It seems easiest to me. Did I do something wrong?
It doesn't look right. I'm sorry. Can I hold it?
Okay, whoops, I think I made a mistake. I shouldn't, this is a great example of why not to do too many steps in your head. So let's clear this up. This really is a minus c over p of c equals 0. I'm going to move this to the other side, so I have b times a minus b is equal to, let's just change the sign here and we'll write this as c minus a over p of c. Does that look right? Okay. All right. Now I can say b is c minus a over the polynomial of c times a minus b. All right. So then we're going to do this. We're going to substitute b into equation 1. Okay, so let's come over here and we're going to do that. So I keep track of this. Equation 1, that's over here. So now I have capital A plus b, and b we just said is c minus a over the polynomial of c times a minus b, parentheses, plus 1 over p of c, this all equals 0. I'm going to add these two fractions first, so let's do that. This is a plus, I have a c minus an a. This is going to become plus an a minus b. All of that is going to be over p of c times a minus b. Still equals 0. Oh, and look at that. That's gonna clean up pretty nicely. I have this nice green chalk. So notice my a's are going to cancel, so I have a c minus b in the numerator. So if I move that to the other side, I can write a is equal to b minus c, b minus c over p of c, a minus b. Parenthesis. Okay, now I have A and I have B. Let's rewrite our complete solution. We're going to rewrite our complete solution. So our complete solution now is, and this is going to be a couple steps. What was our complete solution is A. Oh, A was right there. Goodness. B minus C. I'm going to put this in parentheses, and that's going to be times e to the AT. Plus my b, notice that my b, this has the same common denominator, so plus b, which is c minus a times e to the b t. Okay, all of those share our common denominator, p of c a minus b, plus our particular solution. Our particular solution is e to the c t over p of c. Okay, we're actually making pretty good progress here. This is where it gets interesting. We're going to add this fraction one more time, so I'm going to need an a minus b factor on this last bit of my fraction here. So I'm going to switch my board, so hold on a sec. There. Okay, so we're going to add these two fractions. So when I do that, I'm going to get my complete solution. My complete solution is going to be, we're going to make one big long numerator here. So I have b minus c e to the at plus c minus a e to the bt plus a minus b e to the ct. All of that is over p of c times b minus a. Okay, this is a very particular solution. Did I make a mistake?
A minus b?
Where? Oh, a minus b, thank you. So for those of you that are wondering, my cameraman is also a mathematician and is keeping me on the straight and narrow. So, a minus b. Okay. What do we got? Oh, I remember the problem here. What we're interested in is resonance. So, resonance occurs when C approaches, now it can be when it approaches one of your null solutions, when it approaches one of the null solutions. So my null solutions were lowercase a or lowercase b. It doesn't matter. We could solve for either one. I'm going to just choose a. So resonance occurs when actually C equals a. But what we need to do to study this is we need to sneak up on it, and I will show you why. First off, notice this. So let's just try this. When C equals A, let's take a look at what happens to my complete solution. When C is equal to A, then I have, this becomes, C becomes A. Oh, let's write this out. This is B, e to the a t minus, oh, but C is a now, so this is minus a e to the a t plus, oh, but look at that, a minus a, this whole middle term is just a 0, plus I have a e to the a t, this C is now an A, or is now an A. And then I have minus B e to the AT over, oh, this is where it gets interesting. But now C becomes A, that's my polynomial of A times B minus A. This is where it gets interesting because A minus B. A minus, I don't know why I want to do that. So let's, thank you, A minus B. But we're going to go all the way back to where we started. And that's over here. And what we said is that those solutions to our null equation, the polynomial at that value is 0. But let's look at what we've got. This is 0. That means the whole denominator is 0. And look at this. Here's a b e to the at minus 1. Here's a minus e to the at plus a e to the... we are stuck in this problem right now of having 0 over 0. We can't have that. But the beauty of that is 0 over 0, that's the most basic case where we can apply L'Hopital's rule. And that's what we're going to do next. So notice this. So what we're doing is C is changing. C is changing. So I'll make this note. We're going to apply L'Hopital's rule. Apply L'Hopital's rule, and what we'll do is we're going to take the derivative of this whole, oops, that's a funny looking D. We're going to take the derivative of both the numerator and the denominator, but we're going to do it with respect to what's changing. What's changing is c. Okay, what's changing is c. So I'm going to move my board back, and then we are going to take the derivative of this big numerator here. Here we go. Okay, I find taking a derivative of all of these terms is a real quick way to make a mistake when they're all in these with these factors. So I'm going to start, before I even take a derivative, let's rewrite our y complete. I'm going to write y complete as all this distributed. B, E, A, T minus C, E, A, T plus C, E, B, T minus A, E, B, T plus A, E, C, T minus B, E, C, T. All of that, oh my gosh, all of that is over P of C, B minus A minus B, A minus B. All right, let's take a look. Now, here's what we're going to do. Now the problem is we're going to take, now we're going to take the derivatives with respect to C of numerator and denominator. Numerator and denominator. All right, here we go. Now, C is my variable. So this, I'm going to just write it this way. No, because it doesn't equal anything we've done. We're creating this new piece. This is 0. Let's write that 0. I like writing zeros just for bookkeeping. That's a 0. But here, e to the at, that's the constant, that's the variable. So in other words, the whole derivative there is just going to be a minus e to the at. Plus, here's another case, so this is going to be plus e to the bt, plus, and then that, there's no c's, that's 0, minus a 0, plus, I have to slow down on this one, because notice now I have a c in the exponent. We're so used to thinking of this as like e to the 2x. But now we're thinking of this in the other, the 2 is in my variable position. So my variable is the c. This becomes a times t e to the ct minus, and here it is again, so I can get minus b t e the ct over this c is my variable, so this is the derivative of p of c. C is my variable in this case, times a minus b. And now what we want to do is we want to take the limit as c approaches a. And let's see what we get. This term is unaffected by my limit. This second term is unaffected. These right here, these become a's. And so now look at what I have. We're going to call this our very particular solution. This is the notation our author uses, and you'll see why. Watch what happens. I'm not going to use it quite yet. I'm going to change that. Let's just look at our y complete. So under this case, our y complete becomes minus e, the at, plus e to the bt plus, oh, look at this. I'm going to take a liberty right here, and I've got a common factor. So I'm going to write that as, oh, you know what? We'll do it this way. I'm going to put a big parenthesis here. I ran out of room for my denominator. Plus a, parenthesis, a minus b times t e to the at. All of that is over my denominator, which is p prime of c a minus b. Okay, we're almost there. We are almost there. Now, here's the part that's, what we want to do is unpack this problem. We're going to unpack the fraction. And when we do that, we have, let's see what we have. Our particular solution, in this case, or our complete solution, let's do it that way. Our complete solution becomes, and then we're going to get to our very particular here in a second. It becomes, I'm going to call this, let's do this. You know, I should write it. Let me write that and be more correct. Let's do this. Let's let, I'm going to call it capital D equal P prime of C A minus B. So when I unpack this fraction, this is a common denominator. It's common to this first term, second term, and third term. So I can write this as my complete solution is minus, let's write it this way. I'm going to write it, minus 1 over d e to the at plus 1 over d e to the b t. Now, instead of using d, when I unpack this fraction, notice my last term has an a minus b, and so does my denominator. So I'm going to write that deliberately, plus a minus b t e a t over p prime of c a minus b. Oh, and I just love canceling things. And that cancels. And we cancel that. Now, let's think about, this was our, I should say, this complete solution came from that one unique circumstance. This gave us our very particular solution. So let's write this out. If I was to go back and rewrite this as my complete solution, we'll call this our particular, or I'm going to write it this way. Our very particular solution. And then if we recall that our solution is, it's the null solution plus, in this case, our very particular solution. Well, our null solution, we know, that was capital A, E, A, T, plus capital B, E, B, T, plus, now our very particular solution is all of this. Now I'm going to we'll write it out. Minus 1 over D, E, the AT, plus, I'm using the parentheses just for clarity, because this is a big solution at the moment. 1 over D, E to the AT, plus, I have T e to the AT over P prime of A. Now, here's where this all comes together. These are like terms. So if you had a different solution, you could combine those, and you could just use some C1 e to the AT. If you take and you add A, if you just factor these, A minus 1 over D, it's just some number. It doesn't matter what it is. Plus, if we did that again with our next set of oops, that's a B. I'm sorry, B. If we do that with our next set of terms, then this is just another number, B plus 1 over D. Let's just call it C2. Plus, So, oops, e to the bt plus my particular solution that occurs, which is t e. Now I'm gonna change e. I'll write it this way: e to the at over p prime of a. When you have resonance, one of these terms, one of these solutions match. When they match, it forces in this extra factor of t. And that's where this t comes from resonance. And in general, we write that, remember, this whole problem started with a c, not an a. So we would have written our particular solution as t e to the ct over p prime of c. Okay? And this is something that doesn't normally happen, but suppose that you had repeated resonance, meaning this solution was already one of the roots. You could have another one, and you could have another solution. We'll call it y particular 2. Well, then, if you had another c, another repeated root, you'd have t squared e to the ct over, you take the derivative of the derivative, and you would have double prime of c. And you could continue this out for however many particular repeated solutions you would have. So Pn would be t to the n e ct over the nth derivative of c. Probably not going to happen. In our problems, most of our problems we're going to look at, we're going to have maybe just one or two of these. And in our next video, because I think we're running out of time, in our next video we're going to take a look at where we have an example using resonance. Thanks for watching. See you in the next video.